Thanks for the introduction, and thanks for organizing such a nice tutorial. It is a big pleasure to give a talk here today, introducing myself. I am Yonghyeon Lee, an AI research fellow at KIAS, it's Korea Institute for Advanced Study. And the title of the talk that I prepared is a geometric take on motion manifold learning from demonstration. And for this talk, I prepared a GitHub repository. So most of the figures and experimental results that I share today can be easily reproduced in this GitHub repository. So feel free to check out. And throughout the presentation, in the lower left corner, you can see the codes that generate the contents and some related references. And in the lower right corner, you can see the page number. So it may be useful to remember for later Q&A session. All right, I would like to start by emphasizing that learning a single solution or strategy is not sufficient. The two recent works shown in the slide philosophically argue the same point. An ideal model should have diverse strategies to achieve the given goal, so that if a specific strategy or trajectory becomes unusable, for example, blocked by unforeseen obstacles or environmental changes, we can choose another option. Humans indeed can perform any given task in multiple different ways. Even in the simplest task like grasping an object, we can reach it from multiple directions and grasp it at multiple poses. So I think to be truly generalizable and adaptable like humans, the model should be able to encode and generate diverse trajectories for a given task. And we may be able to use reinforcement learning or LFT approaches. And in this talk, I'm going to focus on the LFT approach, especially using multiple demonstration trajectories. Of course, providing many demonstrations and collecting many trajectories is a challenging task. That's why there is a need for algorithm that can learn effectively from small number of demonstration trajectories. Later in this talk, we'll discuss how geometric methods can help overcome this challenge. In this presentation, we'll use the two examples shown on the slide as our working examples. On the left, you can see collision-free two-dimensional trajectories, and on the right, you can see various SE3 trajectories, SE3 pouring trajectories into the cup. All right, let's start with the simplest setting and assume that each demonstration trajectory is given as a sequence of configurations. So the trajectory here is denoted by X, and each configuration is denoted by Q. And we want to treat this data geometrically. So for geometric treatment, we are always interested in the space of data. So for this case, we need to consider in which space these trajectory data live in. Here, the trajectory space is just the product of configuration spaces, t times, with the sequence length t. This trajectory space is often very high dimensional. It is t times dimension of q. And we typically have small data set. So these two factors introduce significant challenges for learning accurate motion skills. If we attempt to learn like probability distribution directly in this high dimensional space, these methods often fail. On the left, a Gaussian distribution is fitted in the exponential coordinates of the SE3 trajectories. But as you can see, the generated trajectories are significantly different from the demonstrations. We may try deep learning methods, for example, as shown on the right, Riemannian continuous normalizing flows. However, these tend to produce very jerky trajectories that cannot be used even with post-processing because we have small data set. Having said that, we don't need to be disappointed. We still have one reason for hope, namely the motion manifold hypothesis. Imagine multiple trajectories lie in the trajectory space. The motion manifold hypothesis states that these trajectory data points lie approximately on some lower dimensional nonlinear space, a manifold, denoted by M. And the dimension of M is much lower than the dimension of X. For example, the pouring data set, they originally lie in the trajectory space, the product of SE3 spaces. But they do not occupy the entire space it is reasonable to say that they rather lie on some much lower dimensional subspace or a curved manifold. And we may be able to identify this manifold and use it to learn a motion distribution. At this point, one natural question arises. So what's the dimension of that manifold? So how can we identify its dimension? What do you think a suitable dimension of this pouring motion manifold is? The principal component analysis is a classic method for finding the minimum number of variables required to explain the variability in a data set. It identifies the linear subspace that best fits the data set. The PCA algorithm produces eigenvalues and eigenvectors, and we can compute the so-called cumulative explained variance, defined as the sum of m highest eigenvalues divided by sum of all eigenvalues. It is upper bounded by 1 and monotonically increases as m increases. And we can see that when m is about 5, it captures 99% of the data variability of this simple pouring data set. In other words, there exists a 5-dimensional linear subspace that fits this pouring data set almost perfectly. This is good. We've already figured out this data set lies in much lower dimensional subspace than the original high-dimensional trajectory space. However, PCA can only find a linear subspace, and as I said, it is reasonable to guess there exists an even lower dimensional nonlinear manifold inside the PCA linear subspace. Indeed, the dimension of this manifold is called an intrinsic dimension, and there exists many algorithms on intrinsic dimension estimation. There is a good Python library called the scikit dimension, and I tried a few algorithms and they seem to give similar results, around 2. This result indeed matches with what I expected. I initially thought the dimension to be around 2, imagining 2 variables. One is for changes in the pouring direction and the other for the pouring style. I think it's a quite reasonable result. I haven't studied this intrinsic dimension estimation topic deeply, but I just wanted to share an intuitive understanding of how it works. So I brought one example, the Levinas algorithm introduced in Europe's 2004. It is based on the maximum likelihood estimation. Okay, the key idea is consider a closed ball of radius t centered at x, denoted by Sx of t, and let n denotes the number of data points inside Sx of t. Apparently, as the radius t increases, the number of included data points n will increase. Now let's model n as Poisson process with the time varying rate, lambda of t. And the lambda of t is modeled to be proportional with how quickly the volume of an M sphere expands as its radius grows. So Vm times t to the m is the volume of an M sphere, and its time derivative is used to model lambda of t. So idea is that as the ball gets bigger, its volume grows faster. Because of this, the number of data points inside the ball also increases more quickly. And this increase is connected to the intrinsic dimension m. And using observations for n of t, we can fit parameters theta and m via log likelihood maximization. I personally found it really interesting how this algorithm connects the geometric idea of dimensionality with probabilistic methods. It is a good example of the intersections of geometry and probability, in my opinion. Okay, all right, so we now approximately know the dimension of the manifold. So how can we identify the manifold of this dimension? Let me introduce an autoencoder, a generalization of PCA as a method to learn a nonlinear manifold. Autoencoder consists of an encoder and a decoder, and we can use the estimated intrinsic dimension to determine the dimensionality of the latent space. And we find an encoder and decoder that minimize the reconstruction loss so that an encoder maps high-dimensional data points to the latent space, and the decoder maps them back to the original data space, original data points, so the reconstruction loss is near 0. Once these two mappings are well trained, the decoder smoothly transforms the latent space to a manifold embedded in the data space. So the training data points approximately lie on the image of the decoder, which we call a learned manifold. Under some mild regularity conditions, the image of the decoder can indeed be treated as a smooth manifold. That's why we often say that autoencoder learns the manifold and its coordinate chart simultaneously. All right. Okay, now we can apply this autoencoder framework to our trajectory data set, and we define motion manifold primitives. The decoder parameterizes the motion manifold embedded in the trajectory space. Okay, so we learn the motion manifold of a pouring data set. We have 10 trajectory data, and remember the estimated intrinsic dimension was around 2, so we set a 2-dimensional latent space and train MMP. And this is the result. The figure in the middle shows how the trajectory data are encoded in the latent space. We've confirmed that the reconstruction errors for the trajectory data are sufficiently low, so we can tell it learns a manifold of pouring data set. So are we good? I want you to take a closer look at the arrangement of the latent points in the middle of the figure. You might find this result a bit odd. The way the latent points are arranged doesn't really match up with how the pouring direction changes. See how differently these data points are arranged in the trajectory space and in the latent space. Let's imagine how the learned manifold looks like. Remember, the latent space is passing through the decoder and getting warped onto the manifold. It looks like the manifold we've learned is somehow twisted and has wrong connectivity as visualized. In fact, autoencoders often encounter this issue. Consider two-dimensional data points sampled from a one-dimensional manifold, a curve. To learn this manifold, we can train an autoencoder using one-dimensional latent space. And as you can see on the right, imagining two candidate manifolds, two orange curves. In both cases, data points perfectly lie on the manifolds, on orange curves, meaning in both cases have small reconstruction errors. They have indistinguishable reconstruction errors. Therefore, autoencoders can naturally get confused and might learn a manifold with incorrect connectivity. We have addressed this issue in Nurip's 2021 paper presenting neighborhood reconstructing autoencoders, and I would like to introduce this work. Our key idea is to use a neighborhood graph and consider a two nearest neighbor graph for this example, shown in the left. Although the candidate 1 and candidate 2 manifold have indistinguishable reconstruction errors, if we compare them with the graph, we can conclude that the first candidate is an incorrect one with wrong connectivity, whereas the second candidate is the correct answer. So we want to use this graph behind this intuition. So now the research question that we would like to pose is, how can we define a new loss that measures the difference between the learned manifold and the graph? Okay. We define a neighborhood reconstruction loss to address this issue. Let's take a look step by step. Let G be an encoder and F be a decoder. And define a composition map by large F. Then large F of X is a point, we're going to say a point reconstruction of X. And then given a neighborhood set denoted by N of X, consider a neighborhood point X prime in N of X. We define a neighborhood point reconstruction of X prime as follows. The composition F is locally approximated around X by using Taylor's expansion, and it is evaluated at X prime. As an example, local quadratic approximation case is shown in the slide. We can use the linear approximation if needed. Then the neighborhood reconstruction loss for N of X is defined to be the sum of the neighborhood point reconstruction errors. Yeah, this is the definition of neighborhood reconstruction loss. So to understand it, the meaning better, I'll provide a geometric interpretation of the neighborhood reconstruction loss. So for a neighborhood set n of x, on the right, you can see two orange curves, which are two candidate manifolds, as I showed earlier. And green curves represent local quadratic approximation of the manifolds at a point x. So if we use linear approximation, then you can just think of it as a tangent space at those points. The black dotted lines connect neighborhood points to their corresponding neighborhood point reconstructions, and the lengths of the lines represent the neighborhood reconstruction loss. In the first candidate, the green curve does not match well with the neighborhood set, resulting in high neighborhood reconstruction loss. On the other hand, the second candidate has small neighborhood reconstruction loss. So now we can tell the second candidate is a better solution. These are example results from the original paper. On the left, you can see vanilla autoencoder, and on the right, neighborhood reconstructing autoencoders with linear and quadratic approximations. NRAEs learn manifolds with correct connectivity, while vanilla AE fails to learn correct connectivity of manifolds. Okay, so we've applied this method to the pouring data set. So it is now neighborhood reconstructing MMP. In this example, the graph is manually designed, and this is the result. Notice that the way the latent points are arranged matches up quite well with how the pouring direction changes now. We can say that it has now learned a manifold with better connectivity or correct connectivity. Comparing MMP and NRMMP, that we can notice the difference more clearly. We can also reparameterize the latent coordinates to the new coordinates shown on the left, where moving along the x-axis changes the pouring style, and moving along the y-axis changes the pouring direction. This new parameterization can allow us to more easily modulate each vector in the new coordinates. Assuming we have labels for each data point in terms of direction and style, we have found that reparameterization maps by performing interpolations. And as you can see, in the case of MMP, it is difficult to find a good reparameterization map, but NRMMP produces a better reparameterization. So this is a visualization of the two-dimensional pouring motion manifold learned by NRMMP. It shows how the generated trajectory continuously changes as we control the coordinates corresponding to the pouring direction and pouring style. If you look at the pouring style change on the right, at the last stage of the pouring, you can notice that the bottle is rotating along its axis. So it's kind of changing from water pouring style to wine pouring style. Okay, let's move on to the next topic. Oftentimes, we don't want to generate arbitrary motions, but motions that reflect our intent. As a specific example, I would like to talk about language-guided trajectory generation tasks. Let's reconsider our example of the pouring motion manifold. If we told a robot, give me anything to drink, it would be acceptable to generate any random pouring motion. However, if we said, give me some water, then the pouring must be in the style of water pouring, which corresponds to a sub-manifold of the entire motion manifold. Furthermore, the direction of pouring can also be specified. If one were to say, give me some wine and pour it from the center, and as shown on the slide, the motion should only be sampled from a very narrow area. In summary, the motion manifold can vary significantly depending on the input text, and we need to learn this very complex conditional motion distribution or conditional motion manifold. Our strategy is like this. Since we already have the motion manifold and its coordinate space, we're going to learn a conditional density model in the latent coordinate space so that generated latent samples pass through the decoder and become trajectories. In this work, we use a flow-based model, a continuous normalizing flow in the latent space. we train a neural network time-dependent velocity field, which takes a text and the current latent value as inputs. Then samples of a Gaussian distribution follow the velocity field, or the ODE, flowing from time 0 to 1, and ultimately become samples of the text conditional distribution in the latent space. Starting from Z0, passing through the ODE solver, becomes Z1, a sample from text conditional distribution. In other words, given a text input, the latent space prior Gaussian distribution is pushed forwarded to P1, Z-bar text, following the flow of a vector field. One might ask, why not directly learn the flow in the trajectory space? However, as I previously showed, due to the high dimensionality of the trajectory space, this approach results in the generation of jerky trajectories. So that's why we needed a motion manifold learning and learning the flow model in the latent coordinate space. And these figures illustrate how Gaussian samples, starting at time 0, move along the velocity field given text inputs, continuing until time 1. These are all done in the latent coordinate space, learned by the previous neighborhood reconstructing MMP. We can see that the sampling is very successful. I brought this example, indeed, in principle, I believe a flow model can fit arbitrarily complex conditional distributions. So this method will be capable of learning distributions with, or data distributions with complex topologies, such as those with disconnected supports or multiple components, and supports with including holes. So using like flow-based generative models can be a solution to learn such complex topologies. And these are some example results. And as you can see, given various levels of text inputs, our model can generate correct motions. Yeah, for the command, give me a drink, anything please, it produces diverse motions. While the input, give me some wine please, you can notice the clockwise rotation behavior at the end. And when given, give me some water and pour it from the right, it consistently generates motions that match our request. We tested in real robot scenarios, and if there's an obstacle, we might instruct the robot to pour water from the left side so that it can avoid the obstacle and pours water. This is just one scenario. As you can see, our model generates motion, not only pours in the correct direction, but also avoids the obstacle. And we may be able to ask a robot to either pour water or wine, depending on the content. And as you can see on the right, full wine pouring, the robot is kind of rotating its hand. So if we drink wines poured by the wine pouring style on the right, the taste will be much better, right? Maybe not. Yeah. Right. Okay. So far we have been using a discrete time trajectory representation. While this method is straightforward, because data often comes in a discrete manner, but it does have several drawbacks. For example, we cannot compute the time derivative of the trajectory. We cannot compute velocity, acceleration, etc. So this naturally leads to the idea of using continuous time representations of trajectories. So the next topic will be on MMP using parametric curve models. Now, suppose each trajectory is represented by fitting it to a parametric curve denoted by Q tau W, where W belonging to the set calibrate W serves as the curve parameter. And tau of t is defined as a monotonically increasing function of time with time t ranging from some interval. So for example, given a fixed pair of initial and final points, we can use via point movement primitives. The parametric curve model consists of a linear path and a shape modulation term. It is designed to start and end at specified initial and final points. From modulation perspective, there are two advantages of using this model. First of all, it allows the speed to be adjusted by setting any monotonically increasing function tau of t. Second, by adjusting the initial point and the finite point, it is possible to modify the vf points while approximately maintaining the trajectory's shape. So it has a nice properties, and we would like to use this representation instead of discrete representations. Now let's consider the space that consists of all parametric curves, namely the parametric curve space. Notice that this space does not fill the entire infinite dimensional trajectory space. Instead, as represented by a red curved surface on the right, it occupies a finite dimensional space because the curve parameter W is finite dimensional. And these four trajectories can be understood as lying in the parametric curve space XW. In this context, the motion manifold hypothesis asserts that these 4 points lie on some lower dimensional motion manifold, visualized as a black curve inside the red surface. To learn this motion manifold, we can apply an autoencoder framework again, or MMP, to the curve parameter space. You can think of W now just informally as a coordinate space of the parametric curve space XW, as noted. And here's an example result. As shown on the left, consider a 7-DOF robot arm that needs to move from the initial joint configuration to the finite configuration without colliding with the bookshelf. We provide 10 demonstration collision-free trajectories, as shown on the right. And note that each trajectory is fitted to the via point curve model. Again, we've trained MMP with the curve parameter W's. Here's the outcome of the training. First, by adjusting the latent coordinate value z, we can smoothly transform the trajectory along a one-dimensional motion manifold. Additionally, we have the ability to adjust the via points. This allows for changes to just initial or finite configurations while roughly maintaining the trajectory's shape. This is possible thanks to the inductive biases to the via point curve model. Another major benefit of having continuous time reparameterization is that I think it can facilitate dynamic adaptation. Consider a scenario where there's a spherical obstacle in the path, unseen during demonstrations. Now the objective is to navigate to the finite configuration without colliding not only to the bookshelf, but also with the obstacle. And if a planned trajectory is predicted to collide with the obstacle in the near future, it is possible to dynamically replan it in real time. It's done by modulating the latent coordinate value and the time parameter tau simultaneously. Notice that because the robot is confined to the trained motion manifold, collisions with the bookshelves can always be avoided. However, as shown on the right, there might be situations where a solution cannot be found. This could be because the learned motion manifold, which is trained by using only 10 demonstration trajectories, is too conservative or too small. So as a result, it leads to a continuous turning back motion. All right, this will be the last topic. It would have been great if it always worked well, but we've found that MMP++ with parametric curve models fails severely in some cases. Let me show you an example. Consider a set of two-dimensional collision-free trajectories shown in the slide. We've trained the MMP++ using via point parametric curve models. As you can see, the quality of the reconstructed trajectories is good. Now we want to train a probability distribution in the latent space. Looking at the demonstration trajectories, it seems reasonable to train a Gaussian mixture model using 3 components, so we've trained it. However, the generated trajectories fail dramatically. Look at the colors of the X marker points in the latent space. The failure occurs because points of the same color are not fitted into a single cluster. The fundamental reason for this is that the latent coordinate space is geometrically distorted in general. In other words, while points of the same color are close to each other in the trajectory space, they are spread far apart in the latent coordinate space. So in essence, the problem lies in the geometric distortion of the latent space. This issue is similar to the classic problem encountered in 2D world map making. On a map, as you well know, the shortest path between 2 points represented by a straight line does not correspond to the actual geodesic, actual shortest path on the globe. So this problem of geometric distortion in coordinate space has long been a topic of interest in differential geometry. There are diverse maps for each globe, each with different kinds of distortion. Similarly, for motion manifold, there are diverse latent coordinate spaces. And we would want a latent coordinate space with the minimum amount of distortion. So for this purpose, we want to formulate a measure that quantifies the degree of distortion in the coordinate space. That's what we're going to do next. Okay, to do that, let's start with mappings between two Riemannian manifolds. Let M be an input manifold and N be an output manifold with respective local coordinates x and y. A mapping between these manifolds is denoted by F, and its local coordinate representation is also denoted by F, but in italic F. Consider infinitesimal displacement vectors dx and dy in both local coordinates, and suppose the input manifold is assigned a Riemannian metric g of x, and the output manifold be assigned a Riemannian metric h of y. Then we can compute the lengths of these infinitesimal displacement vectors dx and dy as shown in the slide. A mapping F between two Riemannian manifolds is called an isometry, or is a geometry preserving map, if it satisfies the following condition. Denoting J by denoting J the Jacobian of F, which is an n times m matrix, and dy is equal to j dx. If the lengths of dx and dy are equal for all x and all dx, then the mapping F is called an isometry. Because it preserves local distances, local structures everywhere, it ends up preserving global geometric structure quantities as well. The condition can be rewritten as follows, using the fact that the square length of dx is dx transpose g dx, and that of dy is dy transpose h dy. Consequently, if g is equal to j transpose hj for all x, then F is defined to be an isometry, in this case a global isometry. All right, now we know the definition. We would like to formulate distortion measure. Any distance metric between two positive definite matrices G and J transpose Hj can serve as a local measure of distortion. When defining a distortion measure, it is important to ensure that it is coordinate invariant. For this purpose, we can use eigenvalues of G inverse J transpose Hj. I believe we can. It is safe to compute the eigenvalues of this matrix, because this matrix is, yeah, I believe it is correct. Okay, note that if all the eigenvalues are equal to 1, then F is an isometry. Okay, so we can consider any symmetric function sigma that is 0 if and only if all the eigenvalues are equal to 1. Integrating sigma over some positive measure mu leads to a coordinate invariant global geometric distortion measure. Okay, one step further, when training on autoencoder, seeking an isometry can sometimes be too stringent. Indeed, it is intuitively sufficient to preserve only relative distances, and thus we've defined a scaled isometry and a relaxed distortion measure. A scaled isometry is a mapping that preserves angles and relative distances. So to define a relaxed distortion measure, we consider lambda bar an average eigenvalue. Then any functional of the form shown in the slide is a coordinate invariant relaxed distortion measure. You can see the details and the proof in the paper. So the relaxed distortion measure is 0 if and only if all lambdas are equal to not 1, but here lambda bar, or F is called a scaled isometry. Okay, we use the relaxed distortion measure as a decoder regularization term. Specifically, the latent space is assigned the identity metric because we want to use like Euclidean algorithm in the latent coordinate space that is computationally cheaper. We consider a Riemannian data manifold. Manifold is assigned the metric h of x. Then we can compute the relaxed distortion measure for the decoder. Then the decoder parameterizing a lower dimensional manifold becomes a scaled isometry, preserving shapes and relative distances as visualized. These are some example results from iClear paper. With isometric regularization, MNIST images of different classes are placed further apart in the latent spaces, resulting in better clustering. Right, now we want to apply this isometric regularization to MMP++. So it's time to apply this to motion manifold primitives. The first step is to construct a Riemannian data manifold. So for the parametric curve space XW to be a manifold, there are some necessary conditions, some mild necessary conditions. The mapping Q that maps W to the trajectory Q of tau should be injective and emergent. Specifically, if the parametric curve model is affine in W, then if the scalar valued basis functions phi are linearly independent, then we can tell that XW is a smooth manifold. And then as a next step, we can define a natural Riemannian metric for the manifold XW. It is defined as the integral of dq dw transpose dq dw over tau. Then it is a large W times large W positive definite matrix. You can easily understand the meaning of it by looking at how this metric defines the length of dw. It integrates the norm of the configuration's displacement vector dq with respect to tau. And applying the isometric regularization with this Riemannian metric, this is a result of isometric motion manifold primitives. And this is the same example where MMP++ previously failed. In the latent space of IMMP++, we can clearly see 3 clusters where the GMM with 3 components fits very well. And generated trajectories are all nice as well. When compared to MMP++, the distortion minimization effects are more clearly visible. All right, let me give conclusions. So given multiple high-dimensional trajectory data set, we can often reasonably assume that high-dimensional trajectory data lie on some lower dimensional motion manifold, and we can roughly estimate the intrinsic dimension of the manifold by using any of intrinsic dimension estimation algorithm. And that, setting that dimension to the dimension of the latent space, we can learn manifold. We can learn nonlinear manifold using MMP. Note that PCA can only learn linear manifolds, but MMP can learn nonlinear manifolds. Sometimes, as I showed, MMP produces wrong manifolds with incorrect connectivities. And to resolve this issue, we can exploit a graph information. So we can use neighborhood reconstruction loss to learn a manifold with correct connectivity. And when we want to generate motions conditionally, given inputs such as language commands, we can use motion manifold flow primitives, learning flow models in the latent coordinate space. And these methods can learn complex conditional motion distributions. Lastly, using continuous curve parameterizations leads to additional functionalities such as via points modulation and dynamic adaptation. But sometimes there is a geometric distortion issue in the latent space. In that case, we can use isometric regularization to find a geometry preserving latent coordinate space. Okay, these are references on geometric aspects on autoencoders and motion manifold primitives. And the PDF file of this presentation is available on my website. So if you want to review the slides and have some questions, please check it there. Thank you for listening. Feel free to ask any question.
Thank you very much for the great talk. So that we already have questions, so please.
Yes. First of all, I really enjoyed your talk. Congratulations. It was very nice. I have a comment and a question again. So the comment is I see in the last part, when you have a continuous adaptation of the curve, I see a lot of similarity with continuous mechanics. So of the separation of embedding matter in space is something we've been working on. It's very fascinating. So I would like to talk to you if you have a chance later on about that.
Thank you.
And the second question is the fact that you have this problem at the end, where you show that if you have a continuous thing, and is it maybe related to the fact because you have an infinite dimensional search, right? So you have curves in infinite dimensional space. If we have infinite dimension, we know that all norms are equivalent, okay? So there is a unique distance, or let's say neighbor concept. But if you are in infinite dimension, that's not the case. So you cannot say anymore if two curves are close. Is that something it is maybe related to?
I guess I'm not smart enough to answer that question. I know for infinite dimensional case, like infinite dimensional space or Hilbert space, I know there's some undesired issues compared to finite dimensional ones, but
I would be interested to look at that because that is really the problem to go to finite to infinite is the fact that not all norms are equivalent. So you don't have a unique way to talk about neighborhoods. And I think that is where it comes from. I'm not sure, but it's just something interesting to look at. Very nice presentation. Thanks a lot.
Thank you. Thank you very much.
Okay, guys, any other questions?
Thank you for the cool talk. I'm specifically interested in, your work seems to give some intuition or some reasons also about what the latent space variables actually mean for your methods. And I saw you also use the Jacobian map. So I was interested in specifically when you did this stuff with the shelves and you showed how it can be reparametrized. Can you use the Jacobian to actually know how far the latent space variables change the trajectory in the task space?
Oh, right. Indeed, yes. Using Jacobian, let me see the formula if I have one.
So, in a very basic form, can you, if I say I want the trajectory to be, 1 meter to the right, can you do that? Exactly?
1 meter.
Like the goal point, you showed how you can change the goal point. And let's say it's close enough, let's say 1 millimeter, and you just want to shift it 1 millimeter to the right. Do you know or can you calculate the exact latent variable so that the trajectory, the end point shifts exactly 1 millimeter?
Oh, yeah, I think we can do it, but yeah, because Jacobian, given an infinitesimal displacement in the latent space, Jacobian dz exactly maps to, dx in the trajectory space. So if we know units and like metric in the trajectory space, if we can compute the length of dx or geometric quantities of that, I think we can track it in the latent space. But there are some computational issues. But I think fundamentally it is feasible to do this using Jacobian.
Okay, yeah, this would be, I think practically it's an interesting
I see. Thank you.
To just try out, maybe. Thanks again.
Thank
you. Again, your talk was very enlightening, and we enjoy a lot. And I will follow with this comment of the previous speaker. When you are doing robot planning, so you say from here to there, okay, you have a plan, and you assume that the environment is static, right? And so if something moves, so along the path you have few milliseconds to re-plan and avoid the obstacles. So in your approach, you will be able to do that. Is following what he said. Got it?
Sorry, I missed the last part of the question.
Again.
Sorry. Yeah.
When you are doing path planning, okay, you have your robot here and you have to go there, and you have certain path, right? That's normally you assume that the environment is static. The objects are fixed, they are not moving. But if something changes, while the robot is moving, it has to react in a very short period of time in order to avoid this.
Yes.
And can you look at your possible alternatives and change the trajectory?
Yes, that's exactly what it does indeed in this slide. When we're training a motion manifold, like manifold of trajectories, it is the trajectory lying in the motion manifold is guaranteed to not collide with the bookshelf, but it may collide with the obstacle, the moving obstacle, dynamic obstacle in this slide. But in this case, if we assume we know we can detect or we can observe the position and the size of the sphere in real time, then we can replan it. Of course, among the trajectory in the motion manifold, but we can choose an alternative trajectory that does not collide with the obstacle. That's what it does.
So when an object moves, right? For dynamical obstacle avoidance.
Yeah, right.
No,
so
it's great.
It replans it in real time,
Good,
like iteratively replan it.
So we had a last question on the back.
Yeah, so thanks for the talk. So I have a question actually on this. So I come more from, we'll say, more classic robotics perspective. So I have to say, I fail to see what is the advantage of doing this compared to any motion planning that, with repulsive forces and whatever that, I would say, yeah, RTD or, I don't know, splines. So any motion planning among the hundreds that exist that with repulsive forces for the ball, that's, in my eyes, I mean, you will get the same result. So I'm wondering what I'm missing, what you get more than what already exists.
Yeah, I got the point. That's a great question indeed. I think the advantage of course, the downside is that we need a set of demonstration trajectories. But let's suppose that we have a set of trajectories, and then once we learn a latent space or low dimensional space, see the motion manifold dimension here is only two-dimensional. So we can really quickly replan or refine the latent variable z that leads to collision avoidance in dynamic motion planning. So I would say the computational aspect will be the most advantageous compared to the existing methods. And I guess that the advantage will become greater when the static environments become more complex. So traditional motion planning takes longer time. And in this approach will be faster. That's my opinion.
I see. And also, I mean, at the end of the day, anyway, you need something else in the sense, I mean, you're assuming that you have these demonstrations, right? But you're assuming that you have these demonstrations, right?
Yes, right.
But where do they come from? I mean, you need something else. You need like another algorithm which is
That's
able
right.
to solve the problem.
That's
So
right.
you have something that already solves the problem, and then you build, I don't know, another solution to, so where the main point is the computational advantage. That's
Yeah,
what
right,
you
right.
okay, okay.
So like you said, I think one reasonable way to collect this demonstration trajectory is indeed using classical methods of motion planning. And once neural networks are fitted, then we can take advantage of this already encoded model, the computational speed, something like that. Yeah, right.
Okay, thank you very much again for the great talk.
I just